Welcome to Course 3 on Industrial Processing, Module 1, Fundamentals of Food Composition and Chemistry. Today we will explore the essential elements that integrate the food that we process, consume, and are dependent for our nutrition and sustainability. This basic knowledge is fundamental for anyone working in the food value chain. Let's look at the basics of food composition and chemistry. This module is the basis for everything we will study about industrial food processing. Understanding what food is made of, at a molecular and chemical level, will enable you to make informed decisions about processing methods, quality control, and product innovation throughout your career in the food industry. This module introduces the fundamental principles of food composition and chemistry. Understanding these concepts will prepare you to evaluate and optimize processes throughout the food value chain, from production to consumption. We'll examine the significance of each food component, including its structure, function, and contribution, not only to human nutrition, but also to the sustainability of our food systems. After completion, learners will be able to identify the major components of food, including water, proteins, fats, carbohydrates, vitamins, and minerals. Every food product is composed of 6 major components: water, proteins, fats, also known as lipids, carbohydrates, vitamins, and minerals. Each of these constituents has unique chemical properties and fulfills essential functional roles. Together, they determine the nutritional value of food and directly influence shelf life, quality, safety, and environmental sustainability. Let's explore each one in detail. First, water. Water is a polar molecule and the primary constituent of most foods, in some cases like cucumbers or lettuce. It can account for up to 98% of the product. Water serves as a universal solvent where biochemical reactions occur, supports cellular structure, and acts as a medium for nutrient transport. It's crucial for physical, chemical, and microbiological stability, influencing texture, appearance, taste, and shelf life. A key concept here is water activity, which measures the available water for microbial growth and chemical reactions. Foods with high water activity, like fresh meat or fruits, are highly perishable. In contrast, foods with low water activity, such as dried pasta or biscuits, have extended shelf life. Most bacteria require an AW greater than 0.91, yeasts greater than 0.88, and molds greater than 0.80 to grow. Methods like drying, freezing, and salting are used to control water activity and extend product stability. Water determines texture, crispness, tenderness, juiciness, mouthfeel, appearance, shelf life, and influences processes such as gelatinization of starch and protein denaturation. The removal or redistribution of water leads to staling, wilting, or the softening of food products. Water is central to advanced textural engineering. For example, manipulating water states in food matrices allows for tailored juiciness or crispness, as seen in the contrast between fresh grapes and raisins. Next, proteins. Proteins are macromolecules composed of polymer chains of amino acids joined by peptide bonds. There are 20 different amino acids, which means the sequence possibilities, and therefore functions, are nearly infinite. Proteins are vital for body tissue repair and enzyme activity. In food systems, they affect texture, emulsification, and overall nutritional value. Their structure, from primary to quaternary, determines their functionality in food matrices. Protein structure has 4 levels. The primary structure is the sequence of amino acids in the chain. The secondary structure includes local interactions like alpha helices and beta sheets, which form regular patterns. The tertiary structure is the 3-dimensional folding that optimizes stability and function. Finally, the quaternary structure occurs when multiple polypeptide chains join together, like hemoglobin, which has 4 subunits and transports oxygen in red blood cells. Beyond classic gelling or emulsifying roles, proteins like whey and hydrolysates are now used to improve taste profiles, extend shelf life, and even partially replace more expensive or less sustainable ingredients. Engineered protein hydrolysates enhance emulsification, foaming, and water absorption in foods, supporting clean label product design. Protein isolates and hydrolysates are increasingly recovered from food industry co-products, for example, whey from cheesemaking, which lowers waste and creates economic opportunities. Such upcycling supports both nutritional and sustainability goals. Proteins are now used in developing biodegradable materials and edible coatings, reducing reliance on non-renewable packaging and improving food preservation. Moving on to fats, or lipids. Fats are predominantly made up of triglycerides, 3 fatty acids attached to a glycerol structure. Fatty acids vary in chain length and degree of saturation, which influences their physical properties. Fats provide energy, aid in the absorption of fat-soluble vitamins A, D, E, and K, and contribute to mouthfeel and flavor. They are also carriers of flavor compounds and influence food texture in dairy products and baked goods. There are 4 main types of lipids: triglycerides, the most common fat used for energy storage; phospholipids, which are components of cell membranes; steroids, including cholesterol and hormones; and cerides, found in plant and animal waxes. Energy provision. Lipids are stored in adipose tissue and provide energy, 9 kilocalories per gram for the body, especially during prolonged exertion. Cell structure. Essential components of cell membranes, lipids ensure the integrity and proper function of cells. Texture. Their unique physical and chemical properties play essential roles in defining the key texture characteristics, which significantly affect consumer perception and product acceptability. Fats. Lipids are not a homogeneous group, but are comprised of various types that differ in their chemical structure, physical properties, impact on health, and environmental footprint. A clear distinction between saturated and unsaturated fats is essential for informed decision-making by food professionals, both for product formulation and sustainability initiatives. Lipids are highly valued for their nutritional and functional contributions to food, and they are particularly susceptible to chemical changes during food processing and storage. Among these changes, oxidation is the primary cause of lipid deterioration, leading to rancidity, which negatively affects the sensory quality, safety, and shelf life of food products. Rancidity. Oxidation generates volatile and non-volatile secondary compounds, such as aldehydes, ketones, and acids, producing off flavors and off odors, commonly described as rancid, cardboard-like, or metallic. Nutritional loss. Essential fatty acids and fat-soluble vitamins, A, D, E, K, degrade during oxidation, reducing the nutritional quality of foods. Safety concerns. Some oxidation products may be toxic or have unknown health effects. Color and texture changes. Oxidation can cause discoloration and textural degradation in foods, further impacting product acceptability. Fatty acid composition. Higher unsaturation increases susceptibility. Exposure to oxygen, packaging, and atmospheric conditions matter. Processing temperature. Heat accelerates initiation of oxidation. Light exposure. Ultraviolet and visible light promote oxidation. Presence of pro-oxidants. Trace metals like iron and copper catalyze oxidative reactions. Water activity. An optimal level of moisture can either inhibit or promote oxidation depending on the food matrix. Presence of antioxidants, natural or added compounds that slow oxidation. Carbohydrates are one of the 6 major components and serve as a primary energy source. They play crucial functional, nutritional, and technological roles in food systems. Understanding their chemical nature, classification, and behavior is essential for optimizing food processing, improving quality, and promoting sustainability. Carbohydrates influence not just energy, but also texture, shelf life, and even fermentation processes. Carbohydrates are classified by molecular complexity into three main types. Monosaccharides are the simplest, consisting of single sugar units like glucose, fructose, and galactose. These are sweet-tasting and water-soluble. Disaccharides are formed by two monosaccharides bonded together, like sucrose, lactose, and maltose. Finally, polysaccharides are long chains of sugar units, including starches, cellulose, and dietary fibers. Each type behaves differently during processing and digestion. Energy provision: carbohydrates are the primary energy source for the human body. Glucose and other simple sugars are readily metabolized, supplying 4 kilocalories per gram. Textural and structural functions: starch gelatinizes when heated with water, thickening sauces, puddings, and baked goods. Fiber, non-digestible polysaccharides, contributes to the structural integrity of fruits, vegetables, and cereals, and influences mouthfeel and texture. Sweetness and flavor: monosaccharides and disaccharides impart sweetness, contributing to palatability and consumer appeal. Water binding and moisture retention: carbohydrates can bind water, influencing the texture, shelf life, and mouthfeel of products. Fibers especially hold moisture, improving product freshness and delaying staling. Fermentation: substrate, dietary fiber, and some complex carbohydrates serve as prebiotics, nourishing beneficial gut microbiota, thus impacting health. Carbohydrates are predominantly found in plant-based foods. The most common sources include sugars, fruits, honey, sugarcane, and sugar beet. Starches: cereals, wheat, maize, rice, tubers, potatoes, cassava, and legumes. Fibers: whole grains, fruit peels, vegetable skins, and seed husks. Caramelization: sugars decompose at high temperatures, producing color and flavor. Maillard reaction: reducing sugars react with amino acids, creating browning and flavor compounds. Hydrolysis: enzymes, amylases, break down starches into sugars, impacting sweetness and digestibility. Now let's talk about vitamins. Vitamins are a diverse group of organic compounds required in small amounts for essential physiological processes. Unlike macronutrients, vitamins don't provide energy or form structural tissue. Instead, they act as regulators and cofactors in metabolic pathways. Essentially, they help the body's chemistry function properly. They're critical for health, even in trace amounts. Vitamins are classified into two groups. Water-soluble vitamins include vitamin C and the B-complex vitamins, such as thiamine, riboflavin, niacin, and B12. These dissolve easily in water, are not stored extensively in the body, and excess amounts are eliminated in urine. They're also sensitive to heat and light, which is important during processing. Fat-soluble vitamins, A, D, E, and K, dissolve in dietary fat, are stored in body tissues like the liver, and carry a risk of toxicity if consumed in excess. These are more stable during storage but can accumulate. Vitamins are essential for metabolism, immunity, vision, and cell repair. Many are sensitive to processing conditions. For example, vitamin C degrades with heat and oxygen. Cofactors and catalysts. Many vitamins act as coenzymes or precursors for enzymatic reactions. For example, vitamin B6 in amino acid metabolism. Antioxidant protection. Vitamin C and E are key antioxidants, safeguarding cell membranes and nutrients from oxidative damage. Bone health. Vitamin D facilitates calcium absorption, crucial for bone formation and maintenance. Vision and immunity. Vitamin A supports vision, especially in low light, and contributes to immune defense. Blood clotting. Vitamin K is essential for synthesizing clotting factors. Vitamin C, citrus fruits, berries, peppers, tomatoes, and green leafy vegetables. Vitamins B, whole grains, legumes, meats, eggs, milk, leafy greens. Vitamin A, liver, fish oils, milk, eggs, precursor beta-carotene in carrots, pumpkins, sweet potatoes. Vitamin D, produced in skin via sunlight exposure, found in fatty fish, egg yolks, fortified foods. Vitamin E, vegetable oils, nuts, seeds, green vegetables. Vitamin K, leafy green vegetables, broccoli, fermented foods. Finally, minerals. Minerals are inorganic elements essential for life. Unlike organic nutrients, they don't supply energy, but they play crucial roles in biological, structural, and metabolic processes, from bone formation to enzyme function. Even though they're needed in small amounts, their absence or imbalance can have serious health and processing consequences. Minerals are classified by the quantity required. Macrominerals like calcium, phosphorus, potassium, sodium, magnesium, and chloride are required in larger amounts. Trace minerals, including iron, zinc, copper, selenium, and iodine, are needed in minute amounts, but are equally essential. Both groups must be present in balanced proportions for optimal health and food quality. Structural functions. Calcium and phosphorus are critical for building bones and teeth. Magnesium contributes to bone structure and is also found in many plant-based foods. Electrolyte balance and nerve function. Sodium, potassium, and chloride maintain osmotic and ionic balance in body fluids, enabling nerve impulse transmission and muscle contraction. Cofactors in enzymatic systems. Minerals such as zinc, copper, selenium, and manganese serve as cofactors or structural components for numerous enzymes involved in metabolism, antioxidant defense, and hormone regulation. Oxygen transport. Iron is a key constituent of hemoglobin and myoglobin, facilitating oxygen delivery to tissues. Technological roles. Beyond nutrition, minerals such as calcium or sodium bicarbonate serve as acidity regulators, leavening agents, and preservatives in modern food production. Calcium, dairy products, fortified plant milks, leafy green vegetables, canned fish with bones. Phosphorus, meat, eggs, dairy, nuts, seeds, legumes. Potassium, bananas, potatoes, tomatoes, oranges, beans. Magnesium, nuts, seeds, whole grains, leafy greens. Iron, red meat, poultry, fish, legumes, fortified cereals, spinach. Zinc, meat, shellfish, nuts, seeds, whole grains. Iodine, seafood, dairy, iodized salt. Selenium, Brazil nuts, fish, eggs, cereals. To summarize, we've explored the 6 major components of food: water, proteins, fats, carbohydrates, vitamins, and minerals, and discussed how each contributes to nutritional value, processing behavior, and sustainability. Understanding food composition is not just academic. It's the foundation for improving food quality, safety, shelf life, and environmental impact across the entire value chain. I encourage you to revisit these concepts as you continue through the Food Chase project. In the next modules, we'll build on this knowledge to explore food processing techniques, quality control, and innovation in sustainable food systems. Thank you, and I look forward to continuing this learning journey with you.